So there are these two ways of viewing functions. Say we have a function f, and it maps inputs x and y to z. And this is one way of viewing a probability distribution. The probability distribution that's generated by, say, a random stochastic function f can be seen as a projection that measures the relative frequency which elements of the output are produced. Now suppose we have a function f which maps x and y to, say, the square root of x squared plus y squared. And this description we can represent as a graph. Here are the inputs, and each of these nodes in our graph are small functions inside of the symbolic expression. So unlike the extensional view, what this enables us to do is introspect or look inside the implementation of f to see the topology of this graph. Unlike the extensional description where f is a black box, here we can see that f has an internal structure, which we call the intensional description. And this intensional description is a deterministic mapping where, in a sense, we no longer need this data set of x, y, z pairs like we had in our extensional description. We can throw this away entirely and simply use the intensional description to reconstruct these pairs. So one way of viewing a probability distribution is as a collection of points representing the relative frequency which values in the codomain occur. And while we don't have access to the true underlying distribution, we may have access to a data set. And these points we can think of as being generated by a graph. So if we have a PRNG, or a pseudo-random number generator, and we pass those outputs through a graph using a set of nodes which are, say, the internal states of some stochastic transition system. The edges represent probabilities of transitioning between different states, and we'll call this, say, P. Then the output of this process is exactly the probability distribution that we like. However, the problem is we don't have access to the true intensional description of P. We only have access to this extensional description. But we'd still like a way to generate new samples from P. So one way of trying to reconstruct P is to generate a random graph, take inputs from the same PRNG, and compare the outputs of this distribution with the distribution from our data set. And then update the parameters of P so as to more closely match this distribution. And these parameters, theta, can represent either the topology of the graph or, say, the weights of the edges. So one common way of doing this is to take the gradient of this distance between P hat and the true distribution with respect to theta, multiply it by some step size, and then update our parameters so as to reduce this distance. And this process is known as gradient descent, or backpropagation, where this graph is our neural network, this distance function is our loss, and this collection of inputs is our training set.